Welcome back to the next tutorial in the LabVIEW signal processing series. In this video, we're going to look at how we can load in EMG data and perform a basic signal processing chain. Step 1, let's load in the CSV. Go to File I/O, Read Delimited Spreadsheet. Since we know it's a CSV, we'll right-click on Delimiter, create a constant, and type a comma. We're going to need to transpose our data since LabVIEW deals with data in rows instead of columns. So right-click on Transpose, create constant, and then set it to true. Now we need to tell LabVIEW where to find our file, so right-click on File Path and create control. If you notice that your controls are popping up as a big ugly block on your block diagram, you can go into Tools, Options, Block Diagram, and check off Place Front Panel Terminals as icons. Now when you create the terminal, it'll be much smaller and easier to manage. Next, let's remove the first column of data since we know that this is going to be our heading labels. So we'll remove one column of data. So length of 1, index of 0 in the column index. Now, since we're going to want to play around with the settings of our filters, let's put everything into a while loop. A while loop allows us to execute all of our code as long as the stop condition isn't met, meaning that everything will run continuously until we press the stop button. So let's create a stop button by creating a control. If you forget this step, your code won't execute. Now the first thing we're going to do to our EMG signal is we're going to high pass filter it to remove any motion artifacts. This high pass filter is going to utilize a double Butterworth filter, and we're going to set our filter to be between 10 and 30 Hertz. So right click, go into Signal Processing, Filters, and Butterworth. Now we know with the double Butterworth filter, we need to filter the data and then reverse it and filter it again to remove the phase lag, and then reverse it again to get it into the direction we want it. So we'll place our Butterworth filter, hold Control, or if you're on a Mac, Option, and drag, and then we'll right click, go into the Array tab, and we want Reverse 1D Array. So now we'll plug our signal into the filter, plug our filtered X into the Reverse 1D Array, plug that into our next filter, and then we'll copy our Reverse 1D Array, and that'll be our output. Now you'll notice that we have a broken wire here. This is because the filter is only designed to work with 1D array data. What we've fed in is a 2D array of all of our channels. So the first thing we want to do is we're going to break this apart into our signal that contains EMG and our signal that contains our FSR data. We can do that by taking an array subset. So for our first array subset, which contains our EMG data, we'll right-click on the index, create a constant. We want it to start from 0. And we want our length to be 5. We have 5 channels of EMG. Now, because we want to do this filtering operation on each channel, we'll right-click, create a for loop. Now, everything that's inside this for loop will execute on each iteration, meaning that as we put this in, there's going to be 5 channels of data. This for loop will run 5 times. So now there's going to be a 1D array going through every time the for loop iterates. We now need to set our sampling frequency, so we'll right-click and we'll create a constant. We don't need this to be inside the for loop, so we can place that outside. And for this data set, our sampling rate is 1,024 samples per second. So we'll type 1024, and we'll plug that into both filters. Now let's set that we want a high-pass filter. Right-click, create constant, and we'll change this from low pass to high pass, and we can plug this same wire into the other filter as well. Now LabVIEW is a little weird. When we set our filter cutoffs, it doesn't matter whether you're using a high pass or a low pass filter, you're going to plug it into the low cutoff frequency. So we'll right-click and create control. Again, we can place this outside of the for loop. Let's rename this so that we know that it's our high pass cutoff. And we'll wire this into the other filter as well. Now we can wire this out of the for loop, and we're just going to create an indicator. Now, since we know that one of our steps of creating a signal processing chain for EMG is going to be to low pass filter the data, we're going to create what's called a subVI, or a sub-virtual instrument. This works like a function in a normal text-based programming language, meaning that we can call it multiple times to do different things in our data. In fact, it might even be easier if we change our high pass to a control. Now we can select our for loop. We'll click on Edit and create subVI. So this is going to turn this into an icon that we can copy. We know that we're going to need another instance of this for our low pass filter. Now if you double click on this, we can edit the icon by double clicking on the icon here. We'll just delete that. We'll create a nice little case around here. And then in the text, we'll call this double butter. If you want, you can change the color that it's filled in with. And click OK. Now, since we're going to call this same subVI multiple times, we actually need to set a couple properties. So we'll right-click on this icon and go to VI Properties. From the category, we're going to select Execution. From this menu, we're going to select Pre-allocated Clone Reentrant Execution. It just means that we can call the VI multiple times and it won't store the settings from one execution of the VI to the next. Now we can press Ctrl S to save it. And you can see that we still have our two instances of the VI. Now, if you want, you can replace this with a constant so you can see what it is on the back panel. So just right-click and we'll change to constant. And let's not worry about this quite yet because we have one more step. The next step in our signal processing chain is we need to rectify the data. And we're going to choose full wave rectification, meaning we can just take the absolute value of our signal. So right-click, go to numeric, and we're going to select absolute value. Now from here, our next step is going to be to low pass filter the data. So we'll take our double butterworth filter, plug our data in. We can use the same setting for the sample rate, but we'll create a separate control for the low pass cutoff. Note that it's going to be labeled high pass cutoff here because that's what we labeled this control. Now let's set this filter type to be a low pass filter. Making sure that we have our other filter as a high pass. And now let's choose which channel we want to visualize. So we'll right click, go into the array settings, and we're going to index the array. We can create a control on the row index, and this will allow us to choose the channel that we want to visualize. The next thing we might want to do is peak normalize our data. So to do that, we can calculate the maximum value and divide our signal by that maximum. Now we can make it so we can choose whether this happens by using something called a case structure. This case structure is just going to say if we choose to execute the case structure, we'll normalize the data. If not, then the data will be unnormalized. So to set that parameter, we're going to right click on here and we'll create a control. This is going to be a Boolean control, meaning that it can only be true or false. So we'll wire our data in. So in the case that it's true, we want to determine the maximum value. So we can go into array and we'll choose max and min. And now we're going to go into numeric and divide. Take our original signal and put that in the top terminal. And then we'll take the max value and put that in the bottom terminal of the divide. Now we can plug this into the outside or the right-hand side of the case structure. And then we need to set the false case. So when we don't want to normalize, we'll just pass the data right through. Let's take a look at what we've done so far. Press Control or Command E to get to the front panel, and you'll see that we have all of these nice controls over here all stacked together. So let's rename some of these. So this Boolean control is going to be our normalize. Our low pass cutoff, we can right click on that, go to replace, silver, numeric, and we can choose a nice sliding bar instead. Since we know that for our low pass cutoff, we're going to want this to go all the way up to potentially 300 Hertz. We'll set that at 300, and then we can grab the bar and we'll make it a little bit bigger so it's easier to interact with. Let's set it up around 100, and we'll right click, data operations, and make current value default. We can do a similar thing with the high pass cutoff. Right click, replace, silver, numeric, and vertical point slide. Now, if you want these controls to be identical, we can actually delete this, copy this one, we'll rename it to be high pass, and then double click on that, and we'll connect that in where our high pass cutoff needs to go. Press Control B to get rid of your broken wire. Now this index is going to be our muscle selection. And this is our stop to tell our program when we don't want the while loop to execute anymore. Now for our high pass cutoff, we said that we want our maximum to be about 30 Hertz. So we can set that. And let's just adjust our base setting to around 10 Hertz. And we'll make that our default. Now with our current setup, selecting the muscle is going to choose from 0, 1, 2, 3, or 4. If instead we want to use muscle labels, we can do something else. So we can right click So we can right click, go to ring and enum, and we can create a menu ring. If you want a slightly better looking one, we can do the same thing from the silver menu. Now if we right click on here, we can go to Properties, Edit Items, and then we'll enter the muscles in the order that they appear in our data sheet. In this case, we're going to have the muscles in the order of VL, BF, TA, MG, and soleus. But what's happened now is these are all upside down. So this is going to go backwards. We're going to just move these down. And now we have VL, BF, TA, MG, and soleus, just like our data sheet. Instead of having this muscle selection, we can double click on our menu ring. And we can plug that into the index array. And now when we select VL, it'll choose channel 0. When we select BF, it'll choose channel 1, and so on and so forth. If we want the text to be larger, we can select the icon and go up to our application font, size, and let's say 24. Now let's create a graph to visualize our data. Again, we'll go to Silver, Graph, and Waveform Graph Silver. We'll take this graph and put it into the output from our case structure. And then we can choose a file to load. Press Ctrl R or Command R, or you can click on the run arrow. And here we can see that our program is running and we can change the muscle that we're visualizing. If we want to normalize our data, we click the Normalize button. And now you'll see that we're normalized to a maximum of 1 because we've chosen peak normalization. Now let's move on to the next step of our data, which is where we're going to phase average or cycle average our data. To do this, we're going to use the external signal of the force sensing resistor. In this case, we have a heel and a toe sensor. So we'll use the heel sensor to cut up our data into gate cycles, meaning that we're going from heel strike to heel strike. So what we'll do is we'll create a series of EMG signals that start from heel strike to heel strike and they overlap. This will allow us to visualize the average activation pattern over the gate cycle. So we'll go back into the back panel. If you hold Control and drag, you can extend your while loop out a little bit larger. And if you just want to clean things up, you can click on the broom, and if you select a certain subsection of code and click on the broom, it'll only tidy up that piece of code for you. Now in this data set, our heel FSR data is going to be the last channel that we have. So that will be channel 6, meaning it's the 7th channel or the 7th column in our data set. So let's index out that channel. So index array. We'll take our original data set. And we only want row 6. Now what we can do to determine when heel strikes happen is something called threshold detection. So a quick way to figure out where to find your threshold detection is to click into the search tab and type threshold. So you can see that we have multiple threshold detectors here. We're just going to choose thresholddetector.vi. We'll wire that in. And in this case, we're going to choose a threshold of 0.25 and a width of 50, meaning that it's going to search over 50 samples. Now, because we'll want to represent where we've identified these threshold crossings on our graph, what we can do is we can create a for loop. And we'll take the indices of our threshold crossings. We'll plug that into our for loop. We'll take our original data channel, meaning that this is the heel FSR. We'll plug that into the for loop, but we don't actually want to index this. So we'll right click and disable indexing. This means that it's passing the entire array into the for loop every time the for loop executes. Now from here, we'll put an index array. We want to pull out the value of our force sensing resistor at each of these threshold crossings. So we'll index our array at each threshold crossing. Then we can output that to the outside of the for loop. Now, a good way to represent these is on an XY graph, meaning that we give the location as well as the amplitude. So if we want the location, we're going to bundle our location from the indices here with the value that we've output here. To do that, right-click and go into Cluster and choose Bundle. So your X value goes on top and your Y value goes on the bottom. Now we also need to create a signal to plot this against, and that's going to be our channel that we want to view, being our heel FSR. And in order to plot that signal, we also need that in the format of XY. An easy way to do that is to create a for loop, wire your data into that, and now we'll copy our bundle function, and we'll take the index from the for loop. That's going to be our X values, and we'll take our heel FSR channel, and that's going to be our Y values. Now, if we put these together in an array using the build array function, we'll put our heel signal in first, and then our threshold crossings by dragging down to create an extra channel. Now we'll be able to plot that on an XY graph. Now, in order to clean up our code, a good thing to do is create a subVI out of this function. So we can select our code. Before doing that, let's create an indicator. Now we'll select our code, go to Edit, and create subVI. And we'll just call this heel FSR. Now, if we Control E in this subVI, we'll see that we actually have a value that we really want. We want to know what each index that we determined was a threshold crossing. So we'll right-click on that and create an indicator. We'll label this heel strike. And then we need to wire this to the output side. So we can reorganize this so it's a little bit easier to read by going right-click, Patterns. And we're not going to need very many inputs and outputs, so let's just select 2 inputs and 2 outputs. Now we'll plug our heel strike output into the right-hand side here. And let's save this VI. Now you'll notice that it's been grayed out. That's because we changed where the inputs and outputs are. We can fix that by going right-click, relink to subVI. So now we have the output of our heel strike indices here. We'll use this for our cycle averaging. So to choose whether we want to cycle average our data, let's again use a case structure. we'll wire our data into that K structure. And we'll also wire in the indices for our heel strikes. Now, because each gate cycle is going to be slightly different length, we actually need to time normalize them. What this means is we'll identify each gate cycle, but we're actually going to stretch them or compress them so that they all end up being the same number of samples. We do this by creating a ramp pattern and interpolating between our samples. The next thing we need to do is determine how long each cycle is. To do that, we'll take an array subset from the location of each of the heel strikes. We'll wire the constant 1 into the rows. This means it's going to move one sample ahead. And from that, we will subtract the original. So if we create an indicator on there, and we create an indicator of our original heel strike locations, we should see that these are the subtractions of each. So let's just double check. So we can press run. We'll turn on our cycle average. And we see that we have 1337 minus 217, giving us 1120, and that's correct. 2447 minus 1337, 1110, that's also correct. It looks like our subtractions are working. Now our next step is to create the series of gate cycles. To do that, we're going to need a for loop. We'll take our EMG channel, wire that into the for loop, and we're going to disable indexing. Now we'll take an array subset, and we want our array subset to be the length of the difference between the heel strikes. And we want the index to be the heel strikes. Now this looks a little messy, so let's just click on it and we'll clean that up. So what this is doing now is it's saying for each of these heel strikes, create a subset of data that goes from the location of the heel strike for the length until the next heel strike. Now the next thing we need to do is create our ramp pattern. So we'll go up to our search bar and we'll type ramp. We'll click this ramp pattern.vi, and we're going to ramp by samples. We want our start to be 0. We want our number of samples to be 1,000. So this just means that we're going to make our gate cycle 1,000 samples long, which also means that our end needs to be 1,000. Now the next thing we're going to need is our interpolation VI. So again, we'll search for interpolate. And we want the interpolate 1D. Now it's important that we select the National Instruments GMath version of this. Now what this VI needs is our XI, which is our ramp pattern. It needs our Y, which is our original signal. And And we actually have to create an X series, meaning the intervals. So to do that, we'll use the same trick we did before. We'll create another for loop. We'll wire our signal into that for loop, and we'll take the index of that signal and plug that into the X. So this means for each X and Y pair, we want to have a pattern that will give us 1,000 samples over this signal's total duration. And from that, we'll wire our YI out of the for loop, and then also out of our case structure. Now, in the false case of our case structure, we're just going to pass our signal through. Now you'll notice that we can't wire into this other terminal because in our true case, we're going to be outputting a two-dimensional array. In our false case, we want a one-dimensional array. To make our VI run, we need to right-click and select Use Default if unwired on both of these terminals. Now let's copy our waveform graph. Now let's have a look at our cycle average data to make sure it's working as expected. Remember that we'll need to activate this cycle average Boolean control in order to turn it on. We'll press Ctrl-R to run and turn on the cycle average. Now we can see that we've taken the average trace over each of our gate cycles, and it looks like everything's lined up nicely. As we change the muscle, we should get a good representation of the average activation of those muscles over the gate cycle. If we filter our data more heavily, we'll get a smoother signal. What we haven't done is taken a look at the cycles that we've identified with our FSR channel. So to do that, we'll create an XY plot. So go to Silver, Graph, and XY Graph Silver. If we wire this graph into the output we created, that shows our heel channel as well as the identified heel strikes. We can show our second plot on here, which will be the heel strikes. And we'll change the plot type to be a box. Make it a little bit thicker so it's easier to see. And now we can show the point at which we've identified each of the gate cycles when the FSR crosses the threshold that we've identified. The next thing we'll do is we'll calculate the average trace for the linear envelope of the muscle activation. To do that, we're going to transpose our rows into columns and take the average of each column. We'll take our transposed array and wire it into the for loop, and we'll calculate the sum of each element. So we'll go into numeric, add array elements. Now, since we're summing up these elements, we'll need to also divide it by the number of elements that we have. That's going to give us the average. To do that, we can go into our array and array size. We'll calculate the number of elements that we have, even though we know we've set it to 1,000. We'll index out the first value, which will be the 0 index, which represents the number of columns that we have in the original data set, which will be rows now. and then we'll go into our numerics, divide, and we'll divide our summed array by the number of elements that we have, or the number of rows. Now, if we plot that on a waveform graph, we should see that that's the average activation of that muscle. Let's clean up our interface so it's a little bit easier to see everything. Now we can clean up the code so it's easier to read. A good thing to do is add comments so it's clear what's happening at each step. An easy way to do this for subdiagrams is to right-click on them, go to Visible Items, Subdiagram Label. Now, one last final step we might want to take is to calculate the integral of the average linear envelope, or we could look at a fast Fourier transform, but we'll leave that for another day. To do the integral, we can simply take the integral VI, plug in our data, we'll set our dt, or the time difference, and this is going to be 1 over our sample rate, so we have 1024, and then we can go into numeric and take the reciprocal. Now if we plot our integral, we'll see the summed muscle response. And there we have our complete program. Make sure to save your program as well as any subVIs related to it. A good way to save space in your programs is to create subVIs out of every major function. So in this case, we could turn our cycle averaging into a subVI as well. And here we have our finished program for the day. In a future video, we'll look at more complex signal processing that we can do for EMG.